Imagine a kind of matter that manages its own time, a substance that beats to its own rhythm. This is the world of time crystals, a new phase of matter as distinct as solids, liquids, or gases. Unlike traditional crystals, which are ordered in space, time crystals are ordered in time, forming stable, repeating cycles. The idea, first suggested by Frank Wilczek in 2012, challenges our understanding of time and matter. Time crystals suggest that matter can create its own time structure, resisting the usual flow of time. The implications are huge, from quantum computing to the laws of thermodynamics. It's more than just a new material. It's a big shift in how we see reality. The story of time crystals is about finding a hidden pulse at the heart of the quantum world. Time crystals are not perpetual motion machines. They don't defy physics or create energy from nothing. They need a regular push, like a child on a swing, to keep their rhythm going. This push comes from an outside force, like a laser or a microwave pulse. The energy input keeps the system out of balance, allowing its unique time-ordered pattern to continue. What's amazing about a time crystal is how it organizes itself into a stable, collective oscillation in response to this push. Think of it like a musical instrument. The energy is the musician, and the time crystal turns simple actions into complex, structured music. The amazing thing about time crystals is how they break something called time translation symmetry. Usually, if you push something over and over, it'll move at the same speed you're pushing it. But a time crystal moves at a slower, different speed. Imagine clapping your hands every second, but a dancer only moves every 2 claps. That's the special rhythm of a time crystal. The system settles into a new, steady pattern with its own unique timing. Unlike regular stuff that just copies the push, time crystals march to their own beat. This slower, different response is the telltale sign of a real time crystal. It doesn't just follow a rhythm, it makes its own. This really changes how we understand the moving order of matter. Think about a regular crystal. Its atoms repeat in space, forming a pattern. This spatial order comes from symmetry breaking. The atoms choose fixed spots, creating a structure. A time crystal does the same thing, but in time. Instead of repeating in space, its state repeats at regular times. It's like a 4-dimensional crystal, organized in both space and time. This discovery shows that crystallization is a bigger deal. Order can show up in space-time, not just in space. Time crystals reveal that matter can be structured within the flow of time itself. Symmetry is super important in physics. It's how we get rules like the conservation of energy and momentum. But the really cool stuff happens when these symmetries get broken by accident. Think about a pencil standing on its tip. When it falls, it picks a direction, and that breaks its perfect balance. Or how water vapor turns into snowflakes, breaking the symmetry of space. Time crystals break the symmetry of time itself. The system is pushed with a certain rhythm, but it actually wiggles at double that rhythm. Just like a liquid turns into a crystal in space, a quantum system that's being pushed can crystallize in time. It's like breaking symmetry in the 4th dimension. Time crystals are a fantastic example of how the universe can create order even when symmetry gets broken. They show us that even time can have a structure, all thanks to the rules of physics. Making time crystals needs very careful control of quantum systems. One way uses trapped ions, which are held and cooled with lasers. Then, they're made to interact and wiggle together. Another way uses diamonds with special spots called nitrogen vacancy centers. These are tiny flaws whose spins can be controlled with microwaves. These spins talk to each other and lock into a group wiggle, forming a time crystal inside the diamond. Superconducting qubits, which are used in quantum computers, have also been home to time crystals. Each setup keeps quantum particles separate and makes them move, letting that special time order show up. The strong structure of crystals like diamond helps protect the delicate quantum states. These experiments are pushing the boundaries of what's possible in quantum physics. Making a time crystal needs 4 key things: a regular push, interactions between particles, some disorder, and a way to keep it from getting hot. The push keeps the system moving and not settling down. The interactions let the particles work together and move in sync. Surprisingly, disorder, the randomness in the system, helps stop it from getting too hot. This disorder leads to something called many-body localization, which traps the particles and keeps the time crystal's order safe. The result is a bit of a puzzle. A little bit of randomness is actually needed to protect perfect time order. These ingredients come together to make a time crystal that's stable and lasts a long time. In reality, time crystals are delicate and don't last forever. Decoherence, that's when they interact with their surroundings, messes up their delicate quantum state. Random noise and wobbles make the particles lose their rhythm, wearing away the time crystal's beat. Heating is another problem. The regular pushes of energy put energy into the system, and some of it always turns into heat. Over time, the time crystal melts back into disorder, just like ice melts in water. Scientists are fighting these effects with better insulation, super cold temperatures, and quantum error correction. The goal? To make time crystals last from millions to billions of cycles. Every step forward brings us closer to a truly stable and long-lasting type of matter. Time crystals could totally change technology as we know it. Because they're so stable, they're perfect for making super accurate clocks, maybe even better than atomic clocks. In quantum computing, their steady wobbles could be used as quantum memory, keeping information safe from getting messed up. Scientists are looking into new materials and smarter ways to control them. They're hoping to create time crystals that work at room temperature and have even more complex time patterns. This means we're moving from materials that just sit there to materials that are always moving, where their special qualities come from their movement, not just how they're put together. Time crystals are just the beginning. They hint at a huge world of dynamic and out-of-balance states of matter. The future of physics might just be about how matter dances to the rhythm of time.